I'm Mitesh Jain. I work at Synopsys right now. But this work that I'm going to present today was done with my advisor, Pete Manuelis from Northeastern University. So I'm going to talk about runtime efficient way of validating things based on a theory of refinement. So this is what we traditionally do. We have what I'm calling here is a property-based testing. So we have a design and implementation. We define a set of properties, interesting ones that we want to validate. Then we have a test suite, randomly generated directed test. We define what it means for those tests to be correct. And then we execute them and check that the property, if there's an assertion or a violation of the property, it might point to two things. It might be an actual RTL bug or a design bug, and we go forward, fix it. That's great. But it could be a problem with the property itself. So there are a couple, few of the challenges with this methodology that we have. How do we know when we have written enough properties? Like, is the set of properties complete in any sense of the word? Defining these oracles for the test suite is often humanly time-consuming, expensive, and also error-prone. And then if we do find problems with our specification, we are changing the specification, which is obviously always a little dicey thing to do. So for example, for a processor, we might have to write multiple properties that the arithmetic units are computing correctly, the branch and the jump instruction, the branch prediction logic works correctly, the control logic in terms of stalling, forwarding is working correctly, and so on and so forth. I mean, if you were there in one of the Ashish Dabari's talk yesterday for a two-pipeline machine, he had a set of 70 properties that he had to write. And I don't know if they are complete in any, how do we say that? So an alternative to this is what I'm going to propose. But the problem with this methodology was also highlighted by one of the surveys. It's a little old, 2014, but that's the latest I could find and published in some sense. And the thing to note are the second and the third one, which is, I hope it's visible, it's changes in specification or incorrect specification. So these were the root cause of the functional flaws attributed, and it accounts to about 40% of the flaws. So the alternative that I'm proposing here is what is called the refinement-based testing methodology. And the idea is pretty simple. We have a refinement conjecture that I compile that is checked during runtime. And this is a pretty intuitive thing, and I'm guessing most of it would sound almost trivial. But I would like you to see that whatever we do in the testing world in some sense is grounded in some kind of a formal base. So what is refinement precisely? Refinement precisely means that all behaviors of my implementation or the RTL design are behaviors of my specification. So in case of a processor, we are fortunate to have a very good specification, the ISA. And if we do have a golden ISA implementation, and processors today can be pretty complex, but irrespective of what that is, the specification remains the same. And what we want to show is that all the behaviors of this complex pipelined, multi-issue pipeline thing has no behaviors that are not presented by the specification. And that's one property. It's the refinement conjecture that if I were to prove it, it's a complete functional correctness. So what does when we are doing refinement, there are few of the basic things that we have to work with. The two designs, the specification and the implementation are described at different levels of abstraction. So the ISA could be defined in, let's say, C, and that works with decimals, while my processor implementation is a bit vector. There are a number of state components that differ. ISA, for example, has no state, while my pipeline machine has multiple state, including the pipeline registers. They may differ in terms of atomicity of the computation step. So ISA computes an instruction result of an instruction in a single step, while it might take multiple clock cycles. So there are several ways that actually our specification and the implementation differ in the level of abstraction, and the whole refinement should, in some sense, take into account these different levels. And the theory of refinement is pretty mature, I would say. It's been around since 1980s, started with the notion of bisimulation. And over a period of time, there are weaker notions of refinement that have been proposed in the literature to account for more and more optimized design. So bisimulation would have worked in case I don't have any pipelining. But if I do have pipelining, I need to look at stuttering bisimulation or stuttering simulation. And that is fine until I don't have multiple retire in my processor. And then we need a notion of skipping simulation. So this slide, all I want to get across to you that this theory of refinement has been very well studied over the last 3 decades and actually been pretty useful in formal verification of relatively complex systems. So several versions of microprocessors have been verified, not commercially, I would say, but at least in the academia. Compiler verification has used this refinement thing. So CompCert is a pretty well-known example of a verified compiler. There are distributed concurrent systems that are verified using refinement. And microkernels, so Cell4 uses the notion of refinement to verify their stuff. So there's a precedence of the theory of refinement being pretty successful in verifying not just simple blocks or something, but good complete systems. And one of the main reasons for its success in a theorem-proving world or a formal verification is that all of these notions offer what we call the local characterization. To understand what it means is probably a good way to understand a processor is that it's a non-terminating system. So there's a reset state that we begin with, but there's no end state as such. So these are reactive systems. But if you want to reason about these infinite behaviors, it becomes extremely complex. And what the theory of refinement and their local characterization afford you to do is to just reason about single steps. So to make it a little more concrete, this is a local characterization of skipping simulation. So on the intuitively, you can look at, like on the left side is the implementation, and on the right side is your specification. So S and U's are the states of your implementation, and W and V's are the states of the spec. So what this diagram shows is that if I ever start in related states, that is S and W are related, and if I take a step in the implementation, they are one of those 4 possibilities that should happen. And please ignore the formulas for now. I'll try to get to them. But the thing to see here is that we are always reasoning about just one step. So current state and the next state, those are the only consideration. And this, if we were to prove these 4 conjectures in some sense, I would be able to say that all behaviors of my implementation are behavior of specification. And the behaviors are infinite traces in general. And this has other benefits. So just taking this, so this was, if you recall from the slide, this was the weakest notion. And now you can adapt these 4 conjectures depending on the domain that you want to apply to. So for example, if I have a single issue machine and there are no multiple retires, I actually don't need this to be verified. If my specification does not stutter in the sense that it doesn't have, for example, pipeline, as is the case for our ISA, we don't need to include this. Now, what this gives us is simple two things that if we were to verify, we would prove the functional correctness of the design. And now from here, the idea was pretty simple. How about taking this refinement conjecture and just turn it into something that we test? instead of formally verify. I mean, all of you who has used formal can attest to that this can be a long and tedious process, and I can assure you proving refinement is way more involved than proving any single properties. So all I've done here is take this diagram and convert into a simple algorithm, which is a simple checker which is checked on any test case that you run on your design. So the setup is the following. I have my specification, obviously it needs to be executable, and my implementation, which hopefully is executable. And I check this conjecture. So it takes the current state of my system, implementation, and number of cycles to run. And there are two things, which is the refinement map and the rank function, which I'll get to a little bit. But then I check the following. If there is an abstract state that can actually match the one step of the concrete system. If not, well, here is my bug. There's something in the implementation that is observably different from my spec. And notice that now the error is right at the point where the difference appears. It doesn't need to be at the end of the test case where I'm comparing some golden values. So that takes us pretty close, if not very close in terms of the structure of the design as to where the bug appears. And the second case is like the stuttering, which is like saying the register is, the instruction is flowing through the pipeline. And if anything wrong happens there, it tries to catch it. So that's a simple check. And again, it is efficient just because I'm concerned about just current state and the next state. If I were to store anything more, it would become a lot more expensive. So just a very simple evaluation of what it means to apply this technique. I had a simple 5-stage pipeline Soder processor and Spike as my specification ISA simulator. And then I evaluated the approach based on two things. One was how effective it is to catch bugs, obviously. And then another important consideration in any simulation environment is what's the overhead of the checking. I mean, simulation are meant to be fast, and any kind of overhead should be pretty evaluated. So very briefly, I introduce mutations of various kinds. Suppose there's a bug in the decoder part. There's some problem with the stall mechanism in this control logic. There are some pipeline hazards there, or the arithmetic unit is, let's say, instead of addition, I mean, for worst case, it's doing subtraction. Yeah, any wrong in the arithmetic, and then some bugs in the load store unit in terms of data forwarding or not. So with a very reasonable test case, actually, test suite, which comes with a Soder processor, I could detect all of them. So that hopefully convinces you that it's the checker is not worthless. And though I want to say that here that the quality of test suite is as important here. All we are replacing here is the property that needs to be checked. And that does not mean that I can have a smaller test case, test suite to work with. So that's extremely important. The next thing is the overhead cost of this refinement checker. And if you look at that algorithm, there's like 3 primary things that actually we are doing over and above the simulation that is done, which is that we need to compare the 2 states, which often is not too bad. And then there's this notion of a rank function there. And intuitively, what it says is, how is my instruction progressing to the pipeline? Is it making is it taking meaningful steps towards completion or not? And the one in the middle is actually what is the refinement map. And the way to think of a refinement map is it tells you what is observable aspect of the whole design. So I might have multiple pipeline register, but in ISA, in a microprocessor, what is observable is the architectural state. So, but to compute an architectural state of a pipelined pipeline machine to reflect it back is a computationally heavy task. You might have to look into the various pipeline stages to compute this. And so this turned out to be the most important thing in terms of the overhead. And to just give you a little hope here, the choice of refinement map is up to, is what we define and is something that we need to trust. But there are multiple options available here. If you were into one-spin talk, in some sense that refinement was what is called the flushing refinement, where you kind of execute the instruction in isolation to get its effect on the architectural state. But there are other methodologies that you can use, what is called in literature and what I have used is called commitment refinement map, where all you're trying to do is just invalidate all the pipeline registers and just store the PCs there. So if you, the thing to take away from this slide is that if I have a reasonable refinement map and I play with it, you can actually make this reasonably fast. And in my experiments, I could get it down to a linear, like almost a linear overhead of this check, so of this checker, depending on the refinement map that I used. So I'll quickly conclude here. So this is an alternative testing methodology. It is grounded in the theory of refinement. The good part about property-based verification is that if I write a property today, tomorrow, if I use a suitable language to write those properties, I can use it for formal as well. And the same thing holds true for refinement. If I use an appropriate language to describe this checker, this can actually be used to formally verify. And what we get is a full functional correctness if you are ever to do it, rather than incomplete functional correctness. We are lucky in the processor world that we have an ISA model, which serves as a specification, and we should definitely leverage on it more. And since this is one check, the hope is that this is way more robust than like thousands of properties if you ever to write in terms of specification changes. So if you recall, the 40% of functional flaws that are being attributed to the change in specification, hopefully we can negate it. And I guess that's it. Thank you.